Hi, my name is Stephanie Lauber, and this year I will be presenting my work on benchmarking projected Hartree-Fock as an approximation. I've been doing my work under CSRC and under the advisement of Dr. Calvin Johnson in the Department of Physics. So with nuclear physics, we always have to zoom out to this big picture. We have here on the left the current chart of known nuclei according to the NNDC. This was taken in February 2021, where we can see stable nuclei in black towards the central region, with the nuclei becoming less stable as we venture towards the proton and neutron drip points. Currently, the best way to do these calculations, or rather the most computationally accurate way to do these calculations, is through something called full configuration interaction. And this seeks to describe the behavior of nuclei over a wide range of masses, but often we're limited by our computational resources. Either the model space grows too large, or the number of protons and neutrons within our nuclei becomes too large to calculate. So we need to turn to approximation methods that offer a way to calculate important information that we still need for nuclei outside of these current computational limitations of full configuration interaction. The first step to doing this is comparing our full configuration interaction results to our chosen approximation method. And for this, we will be using projected Hartree-Fock. The basic benchmarking was done in the SD and the PF shells. And once we had the benchmarking in place, we turned to two specific areas of interest, germanium isotopes, which are known for having complicated spectra, and something called shape coexistence, which is evident in second and sometimes third low-lying 0+ states in even isotopes. And we also looked at magnesium 40, which is the currently is the most neutron-rich magnesium isotope that has been experimentally created. And this was first measured in 2019. But unfortunately, due to its size and the model space we would need to do the calculation in, it is currently untenable with full configuration interaction. So the primary goal of the benchmarking portion of the study was to determine how well we can compute with projected Hartree-Fock results similar to full configuration interaction in terms of energy spectra. So just briefly, I'll go over the results that I did show last year. This is for germanium with even nuclei. So we can see here on the left in blue is just using a single projected Hartree-Fock minima. The middle in black is our computational benchmark. This is our full configuration interaction results. And on the right-hand side of each of these graphs in red is the results with adding a second Hartree-Fock minima. In all four cases, we were able to produce a second 0+ state. Like I mentioned before, this is quite common in germanium nuclei, which show evidence of shape coexistence. And the original spectra for germanium 66 and 70 are rotational, but with the addition of the second Slater determinant in projected Hartree-Fock, we were able to more accurately recreate the complicated spectra that we see with full configuration interaction. So this is a great improvement with just a little bit more computational time and a little bit more information about the nucleus. Now going forward, we need to look towards parallelization. So with this benchmark in place, we want to move on to larger nuclei and larger model spaces with the ultimate goal of calculations in the no core shell model space. So this means we have all particles participating in our calculation. We no longer have a frozen core with valence particles like we would in our original calculations above and in our original paper that we submitted last year. So we're going to approach the problem of parallelization in two ways. We can look to on-node parallelization with some kind of thread-based program. We've chosen OpenMP for this. And we also want to be able to parallelize across multiple nodes to more efficiently break up the problem. And for this, we've chosen to use MPI. A combination of these two, which is currently in process, will not only allow us to do our calculations for larger nuclei and larger model spaces, but we can build in more correlations by adding more nuclear information. In this case, that information comes in the form of Slater determinants as our input information for our calculations. Finally, once that parallelization is in place, we can also compare the wave functions. So previously, we just looked at the similarity between the nuclear spectra between PHF and FCI. But what I have done under the aid of Dr. Johnson is create a script that actually extracts the density matrix elements that are produced by these two methods. And we can calculate kind of an overlap between the two results. So below is a simplified form of the overlap, but it just ends up being a product of these density matrices, their traces, differences and some normalization factors that I did not include in this slide because it gets a little convoluted. But this script will also allow us to compare directly the transition strengths for electronic and magnetic transitions, just to further prove the robustness of our projected Hartree-Fock approximation. Because again, this is the approximation that we want to take to that no core shell model limit. So we want to test it early on to make sure that it is as robust as we believe it is based on our first paper and based on some preliminary results that were not included in this presentation. Thank you for your time. Again, my name is Stephanie Lauber, and I hope everyone else has a very good ACSESS 2022.